Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this section of the course, we are going to extend our understanding of temporal difference methods. In particular, you know that what we've covered so far is called TD0, and that there is a more general form called TD Lambda. This section is all about how to extend TD0 so that we can get TD Lambda. As you'll see, TD Lambda gives you a trade-off between one-step learning methods, like TD0, and calculating the full return, like Monte Carlo. The first thing we need to learn about when discussing TD Lambda is the n-step method, which is what this lecture is about. The n-step method works as follows. We know so far that the value function can be described recursively. We also know that we can estimate v by averaging the returns for many different episodes. And we also know from TD0 that we can estimate g itself by using our current estimate of v. It's worth asking, what is the most accurate thing in this estimate of g? Well, that would have to be the reward r, because it's an actual sample we got from our experiment. So it's plausible then that if we use more r's and less of v, that our estimate of g becomes more accurate. For example, instead of taking the first reward and then using v to estimate the rest, we can take the first reward and the reward after that, and then use the next v to estimate the rest. Remember that Monte Carlo is just the extreme of this, where we don't use v at all. Note that we can superscript g to tell us how many r's we're using. So you see how this gives us sort of a discrete transition from TD0 to Monte Carlo. Since Monte Carlo learning means that the agent can only be updated after the episode is over, and TD0 means that the agent can be updated after one step, then using n steps of the actual rewards means you'll have to wait n steps before your agent can be updated, so that you can form the target using the actual rewards you got. In general, if we want to use n steps of r, we would create the target as follows. For updating v, if we're doing the prediction problem, the update equation doesn't change. The only change is to g itself. The only thing you have to do is wait n steps before you can update v for the state you are in now. The same thing of course applies to both tabular methods and function approximation methods. This of course can be extended to the control problem as well, where we use q instead of v. If we're doing sarsa, the update will be in terms of the chosen action, and the chosen action will always be greedy or epsilon greedy with respect to q. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to implement the n-step method for mountain car. We are going to make use of the Q-learning script for mountain car that we already wrote, in particular so we can just focus on the n-step parts. If you don't want to code along, although I highly recommend you do, the relevant file for this lecture is nstep.py in the subfolder mountain car. At the top we have all our usual imports. I've also imported a few things from the Q-learning script. Next, I've defined my own SGD regressor. I found that for this problem, it works better than the SGD regressor from scikit-learn. This is the same implementation you saw before, except I've had to change the constructor to accept any argument. The weights are also initialized in the partial fit function, as they are in scikit-learn's SGD regressor. Next, we have the play1 function. Make note of the fact that this is more complicated than our previous play1 functions, due to the fact that we have to keep track of the n most recent rewards, states, and actions. At the top, I've initialized all the usual variables, and also a multiplier, which is used for the n-step calculation. We know that the multipliers need to be gamma to the power 0, gamma to the power 1, up to gamma to the power n minus 1, so it's best to just calculate that beforehand. Inside the loop, we sample an action and perform the action as usual, but now we also have to keep track of the state's actions and rewards. When it comes time to do the update, we need to make sure we've collected at least n rewards. We then multiply our last n rewards by the multiplier we created earlier, and then add this to the rest of the value prediction. Once we're outside the loop, keep in mind that there are still some states that haven't been updated, so we need to update those. Remember that in newer versions of Gym, the episode stops at time step 200, regardless of whether or not you reach the goal. In older versions of Gym, you just keep going until you reach the goal. So it's difficult to know whether you hit the goal or not unless you check the documentation. The documentation says the goal is reached when the position reaches 0.5, so that's what we are checking for. If we hit the goal, then any subsequent reward can be considered 0. If we haven't hit the goal, then we have to make the assumption that we wouldn't hit the goal in the next n steps, and so we set any subsequent reward to -1. That's why I've named this variable guess rewards. After this, we have the main section, which you should be familiar with from before. Let's run this and see what we get. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to discuss TD Lambda as a generalization of the n-step method. Lambda is a parameter that is associated with a vector called the eligibility trace, which we'll be learning about in this lecture. You may have noticed that the code for the n-step method was pretty complicated. In particular, it's not so straightforward to keep track of the last n rewards all the time. Lambda allows us to use a more elegant method of choosing a trade-off between TD0 and Monte Carlo. In particular, we won't have to keep track of the last n steps, and we'll be able to make updates without having to wait n steps, and instead just wait one step like in TD0. We'll see that lambda equals 1 corresponds to Monte Carlo, lambda equals 0 corresponds to TD0, and any lambda in between is a trade-off between the two. So first, let's further generalize the n-step method. Remember that we can define different g's depending on how many r's they depend on. A strange idea might be to form a return that is a combination of these g's. For example, 1/2 g1 plus 1/2 g2. Now, to take that strangeness to the next level, consider that we can sum up any number of g's, even an infinite amount of g's. The only requirement is that the weightings for each g have to sum to 1, since the final g must be on the same scale as the original g's. For the TD Lambda method, the lambdas are given very specific values. In particular, they decrease geometrically. And now if you notice, these don't sum to 1, since the first weight is already 1. So they would need to be normalized. In particular, we are interested in normalizing this for the case where n is infinity. From calculus, we know that the sum of these lambdas is 1 over 1 minus lambda, and so we should scale the sum of returns by 1 minus lambda. We call this the lambda return. You may want to pause the video to write this down on paper to convince yourself it's true. Once we have our lambda return, we can assume our episode is going to end at some point. Let's call that time step capital T. Because we're counting from n equals 1 to infinity, when n reaches capital T minus lowercase t, the n-step return is really just the full sampled return, g of t, with no superscript. So we can manipulate the lambda return to separate the shorter n-step returns and the full sampled returns. We can manipulate the second term until we're left only with the part that depends on n inside the sum. Now the next step is, if you manipulate some of the identities related to series, you can solve for the second sum in closed form. So now we have an expression for the lambda return in terms of all the n-step returns that go up to the end of an episode and then the full return. Pause the video if you want to understand this derivation. I would recommend walking through it using a pen and paper. What you should notice about this equation is that when lambda is 0, we get the one-step return, since 0 to the power 0 is 1. This is TD0. When lambda is 1, the first term is just 0, and so we get the full return, which is the Monte Carlo method. Any lambda in between will give you a combination of all the n-step returns with a geometrically decreasing weight. At this point, the obvious question is, this seems worse than both Monte Carlo and the n-step method in terms of computational effort. With Monte Carlo, all we need to do is compute the returns for the episode. With the n-step method, we have to compute the n-step return for every time step. But now we have to compute the Monte Carlo return and all the n-step returns from n equals 1 all the way to the length of the episode. This sounds like a lot more work for what is not clearly a benefit. Now the next step requires some mathematical wizardry, which is definitely outside the scope of this course, so no proof will be given. However, this method has been around for some time, so you should have no problem searching for papers that discuss it. This algorithm we're about to look at is in fact only an approximation to using the true lambda return that we just talked about. We of course don't actually want to use the true lambda return in any practical scenario, because that would mean calculating all the different n-step returns and the full return. First, let's recall what our parameter updates look like when we're doing TD0. We have our target, which is r plus gamma times v at the next state. We have our prediction, which is v of s. And we have the difference, which is the subtraction of those two. This delta is called the TD error. This helps us tighten up the notation a little bit, but this is still just plain gradient descent. To implement TD Lambda, we need to introduce the idea of the eligibility trace. The eligibility trace is a vector the same size as our parameter vector theta. Essentially, it keeps track of our old gradients much like momentum in deep learning. We define the first eligibility trace as 0, and then every subsequent eligibility vector will be the current gradient plus a fraction of the old eligibility vector. This fraction is just gamma times lambda. Basically, lambda just tells us how much of the past we want to take into account. We can then redefine the parameter update step to use the eligibility vector rather than just the gradient. Recall that momentum in deep learning works very similarly. We keep a velocity vector, which is the sum of the most recent gradient and part of the old velocity. Then we update theta to go in this direction, like how r theta goes in the direction of the eligibility vector. Notice how, because the update for theta now only depends on the next state, we can do our updates at the next step rather than waiting n steps like in the n-step method. But also remember that this is just an approximation to using the true lambda return. One distinction that is made sometimes, because the n-step method and true lambda return require looking ahead to later states, we call this the forward view, whereas TD Lambda, we update our current theta based on past errors, so we call this the backward view. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to implement TD Lambda in code. We are going to take the same approach as the n-step script, where we import most of the stuff from the earlier Q-learning script. One thing to keep in mind as you look through the code is how much simpler it is than the n-step method, even though theoretically it's more complex. If you don't want to try to code this yourself, although I highly recommend you do, the relevant file in the course repo is tdlambda.py in the subfolder Mountain Car. At the top we have all our usual imports. After that we have our definition of the class base model. This is like the SGD regressor we wrote earlier, but I don't want to call it SGD regressor since it's now using eligibility traces. I've renamed some of the arguments in the fit function so that you can see what's what. Predict is the same as usual. Next we have the model class. This is going to be a little more complicated because we have to keep track of the eligibility vectors as well. In the constructor, we initialize a base model for every action and an eligibility vector. The predict function is the same as before. The update function is where all the big changes are. First, remember that part of the eligibility vector update is just gamma times lambda times itself, so we can do that first. The next step is to add the gradient, which we know is just the feature vector itself. The sample action function is also the same as before. Next we have the play1 function. I don't think anything in here should be surprising. It's all stuff we've seen in previous scripts. We have an additional argument lambda which is as expected, but we are still doing Q-learning. Notice how much simpler and shorter this is than the end-step method. We no longer have to keep track of all the rewards, nor do we need to do a catch-up loop to run through the rest of the states after the episode is over. Next we have the main section, which is exactly the same as before. So let's run this and see what we get. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture we are going to summarize what we learned in this section. In this section, you learn reinforcement learning techniques that can be applied to any situation where you would use regular Q-learning or SARSA. And so while the examples we did were very specific, know that they are more like general tools that you can test in a variety of situations. Although it may not have seemed like it, we technically got some more practice with RBF networks as well, since that was the underlying feature expansion we used for this script. It is convenient that these kinds of details can be abstracted away, so that you can focus only on the new parts. First, we looked at end-step methods as a generalization of TD0. TD0 is a one-step return because it uses one sampled reward. But we saw that we can use any number of rewards in our calculation of the return. In particular, using n rewards gives us the n-step return. If we take n all the way to the end of the episode, we are doing Monte Carlo. Next, we saw that we could combine all the n-step returns up to infinity, and this gives us the lambda return. This is for the situation where we weight each n-step return by a geometrically decreasing lambda. We saw that by manipulating our expression for the lambda return, that lambda equals 0 corresponds to TD0, and lambda equals 1, which we call TD1, corresponds to Monte Carlo. We then looked at an online algorithm using eligibility traces that approximates online TD Lambda. It is interestingly reassuring that the TD Lambda algorithm looks a lot like the momentum update from deep learning. Think of these as new tools for your toolbox, like all the other algorithms you learn in this course. It's not guaranteed that any particular algorithm will work for your problem, but the more tools you have, the more things you can try, and the more likely it is that you'll come across a solution.